All right, so this one says calculate mentally, which I think a lot of math students, when they see that instruction, they're like, oh shit, but let's do one example here. Yeah, so here's 8 and 2/7 minus, what was this, 2 and 6/7. So this says calculate mentally. Obviously, you can write down your thoughts, but what's the immediate kind of issue with this? Why is the answer not 6 and something? This number's almost 3, and this number's just above 8. So the answer's not going to be 6 and something. It's going to be 5 and something. Do you guys, there's an official kind of way to do this using borrowing. Does anyone know a different method? Yeah?
Don't you take a 1?
Totally, that would be borrowing, yeah. So kind of the official way is if I take a 1 away from 8. So here it is. There's the 1 I took away from 8. I took it away and I put it over there. What else is 1? 1 is also 2 divided by 2, right? 1 is also 4 divided by 4. But in this case, what's the best way to have 1? 7 over 7. Because now I can take a 1, that 1, and I can give it to this guy. Yeah, so that's the official way to do this, right? So this will be 7 and 9/7. And it's kind of good if a little piece of you kind of recoils, because this is something that we normally shouldn't write, correct? If this was somebody's answer to a problem, that would be wrong. You guys agree with me? It is the right number. It is totally the wrong format. But this is the exact same thing we do, of course, when we have like 82 minus 19, and I borrow a 1 and I overload this. There's no way 12 can be there. But it's not really there, right? So here, there's no way this should be 9/7, but it's not really, because it's going to lose shit in a minute, so it doesn't matter. I gotta overload it so I can have something left. Okay. So then, of course, I get, what do I get? 5 and 3/7. All right. Anybody have a different way to look at it? Or are you guys like, dude, we got it? Why would we need another way?
I'm looking at it, and you could do like, no, actually, never mind.
Okay. Jeff, it's not a power. Let's not make this freaky. All right, guys. So real quick, we're just going to explore this. Yes?
Could you add 1/7 to both? Because then it would equal the same distance between the two.
I love it. So we could do sort of the equal additions method, right? So if I add the same thing to a subtraction problem, to both parts of a subtraction problem, the distance stays the same. And why did you say 1/7? Because that would make
The 2 and 3.
Yeah. So if I add 1/7 to both of those, the answer to the subtraction problem is the same. So then this would be 8 and 3/7. Jeff, I don't know why you want to make that a power. That would suck. Minus 3, and then that's easy, right? Definitely easier. So that would be 5. And then the 3/7 is left over. Same answer, thank God. Right? So it's the same idea as like 46 minus 19, so you make it 47 minus 20. So then it's just easier. There's no borrowing needed, right? Kick ass. Here's a way you don't see very often, and I wouldn't recommend it, but I'm just going to show it to you. Jeff. So 8 minus 2 is 6. 2/7 minus 6/7 is negative 4/7. You guys agree? Of course, you wouldn't see this quite yet because we're not dealing with negatives in this book yet, but I don't care. This is the idea I'm going to show you. What's the quick way to do 4/7 less than 6? You kind of think backwards. It would be 5 and something, correct? It would be 5 and the thing that would make 4 sevenths 1, 5 3 sevenths. So you get the same answer again. Of course we do, right? It's all math. It's got to come out to the same answer. Okay, maybe. Again, I'm almost certain you guys have never seen that method. Because that's weird. I wouldn't show somebody this method the first time, right? But back when I was allowed to teach Math 90, I would show people this, just to kind of push their brains a little bit, show them there's other ways to look at things, right? This way is really nice because it's something we've done before. And this way is also nice. This is a good way to do it because it reinforces several things for a student. So let me talk about that real quick. As a teacher, there are very often a lot of methods to do something. The reason you pick one method over another, there could be multiple reasons for it. Sometimes I'll pick a certain method to do something right now because the more practice they get with that, it'll help us out later. So this happens a lot in algebra when there's a lot of different ways to solve a problem, but if I have them solve it a certain way, that's a lot of practice for when that's the only way that'll work. I don't want to get too specific because I don't want to suddenly make this an algebra class, but anyway. You could also pick a method because maybe it's more work, but each step is something they have to have practice with anyway. Does that make sense? You guys with me? So that's a whole other level of thought process behind exactly what to show students that you guys are going to have to kind of consider. Where are we right now? What do I need them to work on? That's going to inform what method I want to use right now. And then later you can show them some other methods, right? Okay. Anything else I missed? Anybody else have a different idea how to do this problem? Okay. These are all the ones that come to my mind, but there could always be more. Anything else from homework? I don't know if that was enough to help you with that whole section. I just took one piece of it, but they all should be very similar. Yeah, okay. Anything else? Okay, no, okay. So I think last time we didn't quite finish 6-2. So I want to finish 6-2. We're going to watch some more kids doing stuff. And then we're going to talk about 6-3, and then we're going to head out. So today, unfortunately, for you guys, is a lot of me talking. So too bad. All right. We're like just a little bit behind. We're not really that bad off. And again, we were behind from before. So in that case, we're sort of like right on track from that. And in case you came in after I wrote that down, there's a quiz next Tuesday. So the last couple things. How would you, for subtraction, this might be something I already talked about. I don't think I did. How would you model this visually for a student? Did we talk about this? We did? Okay, good. Did we talk about, so real quick, just this is good. So you always want to overlap a little bit. So you could do, there's 3/4, right? Minus 1/4, right? So then you can physically, this just comes out of this. This just comes out, you're out. So now I get this, 2/4. And then of course, how would you show visually how that reduces? I mean, just looking at the picture, how much of the picture is shaded? Half of it, yeah. So you could, a student will look at that and they'll say 2 out of 4 because they're kind of like trained. 4 parts, equal parts, 2 of them are shaded, that's 2/4. But then you say, okay, step back from that. Think of this as, you know, get them to say that's the midline. So what half of it's shaded, right? So of course I could just uncut those in half, right? And then that becomes 1/2. Okay. I like it. Kick ass. What about, we might have even done this, I think. Yeah, maybe we did get this far. I didn't think we got here, but I think we did, maybe. before they even know how to do like denominators. How would you show this visually? We start with 3/4 again. But if I do -1/2, yeah, we did do this. Okay, I remember. As I said, it's kind of nice, even before you start to break it up, before you go anywhere near getting like denominators. This is exactly this, correct? And if you had something that was maybe computer generated instead of by hand, it would be even more apparent. So you basically just lose this. So then you end up with that, right? Then you could say, cut these in half. So this is really 2. So you are losing 2. So of course you get the exact same answer. And that also reinforces the opposite of reducing, correct? Because of course, what's the way to do this by hand? You would do 3/4 minus 2/4. And that again is reinforcing building it up. Okay, let me stop for a minute. All right. Oh, yeah, that's true. I did want to do this. I forgot about that. Dadgummit. Yeah. Well, actually, let's do this first. Here. All right. Everybody got that ground shaking stuff up here? Okay. How would you do? Could everybody take a minute? This is sort of related to what we just did earlier, but yeah, just do that. Try to do it all in your head. You can write the problem down and just kind of stare at it, see if you can do it all in your head. Okay, who's got that? Yeah.
6 and 1/5.
Yeah, why?
So what I did was I took the two whole numbers and I added them together and I put them to the side. And then I added the fraction and I saw that I have 6 over 5 and then I turned it into an improper fraction. I added that. And then I got the 6.
All right, cool, okay. So it's basically kind of the inverse of what we did earlier, right? Okay, I like it. Because earlier we overloaded the first guy. Here we put them together and got an overload and then had to un-overload it, right? Yeah. So you can imagine, yeah, I'll get those in a minute. I'm gonna leave this up here. I forgot I wanted the little manipulatives. What about, sure. So I'll let you think about that. All right, so who's got a couple of approaches? Give me one approach. Who's got something they've tried? You're all like, were we supposed to be doing something? Who tried something? What did you guys try? Anything? Yeah.
20 minus 11, and then
Sure.
you get 9. 9 minus 5 ninths.
Okay. So
98.
in the background, what that approach is doing is kind of like remembering there's a plus in the middle of those. And you're like, "Ah, that's not what it is," but that's basically what's happening in the mathematics. And then the negative would distribute, right? So you do get 20 minus 11 minus 5/9. And then this you could do like we did earlier, right? It's got to be 8 and the thing that would add to 5/9 to make the extra 1 to make it 9. So it'll be 8 and 4/9. Did anyone do it a different way? Or is everybody like, oh, we did it that way right there? What about this? You ready? Watch this. This is, Jeff, you can do it, buddy. 20 is also known as 19 and 9/9. Do you guys agree? Ain't no way I would write it like that, right? So this is sort of like the borrow thing, but it's actually a little more direct than that, right? And then you can see it's going to be 8 and 4/9. Same answer. So any approach I take should get the same answer. I love it. How you guys doing? What about thinking about it, missing addend approach? Anyone remember what that means, missing addend approach? What do you have to add to 11 and 5/9 to make it 12? Let's just do that. 11 and 5/9. What do you add to make it 12? 4/9. And then what do you add to 12 to make it 20? 8 and 4/9. Shabam. Right. So it's kind of like thinking backwards about what would I have to add to this dude to make it that dude, and that's one of the very first thoughts we had about subtraction, right? Missing addend. Division was the missing factor approach, right? Okay. So let me show you real quick here. Did I write that? Oh, let me write that one down. You're there. What about 3 and 1, Jeff? Oh, it doesn't matter. You guys got that written down. 3 and 1/6 minus 1 and 5/6. Okay. So just to put this down, because I'm going to do this over there with some manipulatives. So obviously we could do the borrow thing, right? So this would be 2 and 7/6. There's another approach that nobody came up with or nobody told me. And of course this would be 1 and 1/3. So we'll see that happen in a minute. What about changing both of those into improper fractions, right? Yeah. Because then it doesn't matter. This guy is bigger than that guy, correct? It's just that right now this piece is smaller than that piece. But if I force him into improper fractions, I'm not going to have that problem anywhere. So what would this be as an improper fraction? 19/6 minus 11/6, which is 8/6, which is 4/3, which is 1 1/3. Okay, good. All right. And again, please understand, none of this is supposed to be like, look at this, kids, you've never seen this shit. No. We're always talking about how you have to understand it well enough that you can explain it. And also you need to be ready for all the various ways your students are going to misunderstand it. That's the hardest part about teaching. The easy part about teaching is knowing it well yourself. That's the easy part. The hard part is, what the hell did this kid do to get this shit? Right? Don't say that while they're in the room, but you know. So let me show you this. Again, it's nothing groundbreaking. This is why I'm not worried about you all getting some of these. What is it? Okay. You have to turn this on, Jeff. Someday. Here we go. All right. This guy won't turn on unless I'm here. There you go. Oh, let me get something. Oh, shoot. Here. There you go. It's just easier to see, I think. All right, so very quickly. I don't know why this guy, that guy, this thing's been working out. Don't know why. Okay. All right, so real quick, if I wanted to do, what was it? Now you covered it up, Jeff. 3 and 1/6, correct? Is that what that problem was?
Yes.
What was that? What was it?
1 and 5/6.
Minus 1 and 5/6, right?
Mhm.
There we go. So there's, can you guys all see that? Let's put you way up here. There we go. So you guys go away. Go away. All right. 3 and 1/6 minus 1 and 5/6. So we've seen this exact idea before with the flats and the longs and the units, and they kind of like replace it with the individuals. So of course, I can break one of these up, which matches the idea of what? If I replace one of these, did you lay out enough of these, Jeff? I don't know, Jeff. Almost. There we go. There we go. So if I replace this dude with this, okay. So what is that the idea of? Borrow. So now I've got 2 and 7/6. So now I've got to take away 5, and I've got to take away 1. What's the answer? 1? I think so. Oh, where did I? Oh, I took away 2 minutes. There we go. So it should be 1 and 2/6, which becomes 1 and 1/3. And of course, the beautiful thing about this is it's kind of fun just making the shape. So if I were you, if I was teaching somebody and they were going to use these for the very first time, first, let them do whatever the hell they want to with them, right? Make little things, see if they'll lean on each other, whatever. Then say, can you make that shape out of these shapes, right? And I think, I remember the dude did that. Can you make that shape out of this shape, you know? And then it'll be more intuitive about the idea that they break down and they represent fractions, okay? So I just want to show you that real quick. If I wanted to do, here, oh, there is a pen there. Do you work? That's a good question, yes. So if I wanted to do 2 and 5/6 plus 3 and 5/6, your poor little pen, that was it for you. So if I want to do 2 and 5/6 plus 3 and 5/6, you got it, Jeff? No, you can almost count. You're almost there. And again, this just becomes, and we've seen them do this before with the different shapes that didn't represent fractions. So they're very used to this at this point. So they just sort of reorganize. And then here they get to, how many times can you make that shape? There we go. So now it should be 6 and 4/6. Is that right? No. You got to do this slower, Jeff. So 2, and you're all like, oh, good. 2 and 5/6. Let me do this more carefully. 3 and 5/6. There it is, buddy. Right? 1 over 5. 1 over 5. So this will become 5 and. Oh, this is so fun, Jeff. I'm so happy to sit here watching you. Is that what it is? Oh, yeah, there. And 4/6. 5, yeah, 5 and. Oh, this is really fun. All right. Let's try this. 2 and 5/6. I'm gonna get it. I'm showing off how I should be in your class. Plus 3 and 5/6. Okay, just be careful. 2 and 5/6, 3 and 5/6. There we go. There's my 5. And then I put these together. Get in there. Yeah, all these little dudes are different. What do you call it? Different thicknesses. There we go. Okay, so that's 6 of those. Right? Okay. So that's 6. 4, 6. So what should it be? It should be. Oh boy, none of these work. There. So it'd be 5 and 10/6, which would be 5 and 5/3, which would be 6 and 2/3, which is fine, Jeff. Okay, I was just doing it wrong there. So there I would get 2/3. Two of these bad boys. Okay, all right. I kind of went off the screen there. So let's watch people who are better at that than I am. Let me see. Can't remember what this is. Let's find out. Oh, I gotta turn my little dude off. Idea. What would you tell the student that says 1/2 plus 1/4 is 2/6? I mean, how would you start them down the path of understanding why that can't be right? I mean, he questioned himself. I think he knew how to do it. It's a very nerve-wracking situation, I'm sure, but the student who does that and thinks that it's correct, what's one way you could kind of start them to understand why that's not right? Does anyone have a suggestion on what you could show them? Yeah.
Well, you could say that since you only have one fourth, the largest amount of pieces you could have is only 4. So how could you possibly get 6 pieces out of just like the whole 1/4?
Okay. So you could have them represent what 1/4 is and say that a whole would be sum out of fourths.
Mm-hmm.
Okay, I can kind of see that. So where would the 6 come from?
Yeah.
Okay.
I'm like a visual learner, so I would just start off with drawing like a picture and then just showing.
Yeah, okay, sure. And you could have them draw what each of these represents, right? And then just visually see that there's no way they match up. I like it. What if you had to do something for some reason, because like I'm telling you to, not visual, just a purely mathematical explanation why this can't be true? I'll show you my favorite example. So if this is the right math, that means that 1/2 plus 1/2 is what? Apply the same incorrect logic. 2/4, and 2/4 is? So therefore, 1/2 plus 1/2 equals 1/2, right? And normally they would kind of agree, that's not right. So if I gave you half your toys and then he gave you another half of your toys, shouldn't you have all your toys, not still just half your toys? You see what I'm saying? Okay, I like it. Half a cookie, and then I give you another half a cookie. You don't suddenly the half a cookie doesn't sort of like disappear, right? Get absorbed by the other half. Okay, maybe? Okay. And to me, when you're teaching the math part of what you're gonna be doing, I've said this a lot, but that's gonna be the hardest thing and that's the part that takes the most time, is to try to connect with the incorrect way a student's looking, but try to connect them with the right way. So you gotta kind of figure out, where did I lose you? Where's the last thing that actually matches with the way you're supposed to be doing things? So try to connect that. Okay. So let me ask you this. Estimate using front end estimation. Could have said that more concisely, but too bad. 11 2/5 plus 7 4/7. So that would just be what? I mean, front end estimation is very specific. It's not even a range, so what would that be? Does anyone remember front end estimation? It's literally what it sounds like. What are the front ends of those two numbers? Yeah, so the front end estimation would be 18. So front end estimation is always the lower part of the range estimate, right? I don't know if you guys remember that. What would the full range estimate for this be? One would be 11 plus 7. You can do it, Jeff. Is 18. The other part of the range would be 12 plus 8, 20. So then you can kind of give a decent estimate to be 19. Does that make sense? Kick ass. Okay. So that's very familiar to what we've done before with whole numbers. Same idea. Okay. And again, this shouldn't be too surprising. if you haven't looked ahead yet, what do you think the next section is going to be? So we went from whole numbers to fractions. Next section's got to be decimals. I love it. So that's in our future, and we're going to do more estimation with decimals. It's going to work the exact same way. Okay. Oh, so I remember, all right, there is a very obvious physical interpretation of 4 times 2. Would you all be able to come up with a physical interpretation? And what I mean by that, like a real life situation where you have to do 4 times 2. Who can give me one example of that? A word problem you would give a student that they should do 4 times 2 to do. What would that look like? Yeah.
Maybe the strawberries at the store for $4 and I want 2 of them.
Okay. Whoa, this is some damn good strawberries. You mean like the
Yeah.
okay. So a carton of strawberries costs $4, and I want 2 cartons. I love it. So that's the basic idea of multiplication. How about a physical interpretation of 2 divided by a half? Okay, a while back I came up with one. I was very excited, so I'm going to share it with you, and you can tell me it's shit, or you can tell me, oh, that's not bad. Whatever you like, right? Eventually, we're not going to get there. So first thing I want to show you is another way to think of fractions. So one very bad thing about math is that there's very often multiple ways to do stuff. So what I've noticed is students will mix the ways, and that almost never works. So they do a little bit of this one way and a little bit of this other way, and they get weird ass things. So it almost sucks. Have you guys ever heard the phrase paralysis of choice? You go to buy some cereal, and there's 18 billion forms of cereal, so you're like, So what do I mean by that? There's a ton of different ways to look at 6 divided by 2. We looked at the measurement, the sharing. Here's another way to do it. 6 divided by 2 is the number that it takes 2 of to multiply to be 6, right? So 6 divided by 2 represents the number that it takes 2 of to become 6, not multiply, but add up to be 6, right? You guys follow? So that's why it's 3. It's one reason why it's 3, because it takes 2 3s to add up to be 6. So 6 divided by 2 is the number it takes 2 of to add up to 6. So what is 2 divided by 3 then, using the same logic? So 6 divided by 2 is the number it takes 2 of to add to be 6. So 2 divided by 3 is the number it takes. No. 6 divided by 2 is the number that it takes 2 of to add to be 6. Do you guys all agree with that statement? Not like your first level way of looking at division, but that's definitely true, right? 2 divided by 3 is the number it takes 3 of to add up to be 2. Number it takes 3 of to add to 2. Let's check it. So if I take 3 of these, what's 2/3 plus 2/3 plus 2/3? 6/3. And what's 6 divided by 3? 2. Okay. All right. I don't know. Again, the book addresses this, and I like the way it does this. 2/3 could be looked at as breaking up something into 3 parts and taking 2 of them. But 2/3 itself is its own number. It's a number. It doesn't have to be break something into 3 parts and take 2 of them. 2/3 is its own number in its own right. So this sort of reinforces the idea that 2/3 is a number. It's the number. It's the number that I add 3 times to get, what did I say? It takes 3 of to add to be 2. Okay, maybe. All right. So 6/7, what would that be? The number that it takes 7 of to add to be 6, right? So if I try it, 6 sevens. What is repeated addition? So this will be 7 6 sevens, right? Isn't that 6? Right. So that kind of way of looking at it leads to that kind of idea, right? Okay. Okay, so let me see if you can remind me, what was the first visual way we looked at just multiplying whole numbers? So one of the first ways we looked at doing 4 times 3, for example. Visually. Yeah. Okay. Could be. So one way would be the set model. I have, in that case, what would this mean? 4 groups of 3. I love it. What about measurement? What about rectangular array? Right? So this would be 4 times 3. Right? All right. Thank you. Okay. So if I go to do something like, believe it or not, if I do something like 5 sevenths times 1/3, I could do the same thing. Now it's gonna feel, now somebody pointed this out before. This is 12 distinct things. So this is, the way I look at this is like I have a sheet of a brownie and I haven't cut it yet, and then I cut it into 12 pieces. So each thing is its own brownie. You could say this is 1/12 of the whole sheet, correct? But you do not have to look at this as fractions. You could. Now we got these fractions. So let's see if you guys are cool with this. What would be this way? What would be this way? What's on the top? What would be on the top? What was on the top over there? Yeah, so 1/3 would be on the top. So I'm going to cut this like this, and then I'm going to shade. That's 1/3. Right? Now I want to do 5 sevenths this way. Bless you. So I am going to cut it incredibly enough. You'll never guess. What happened? Oh, there you are. You're a pretty good one. Come on. Into 5 parts. It's pretty good for me. 5 parts. You're awesome, Jeff. All right, that didn't just happen. Into 7 parts. And then I want to shade in. How many of those? 5 of those. So I'm only going to shade in. So this is 1/3 says only this exists. I kind of want that to make sense. If I do 1/3 of something, the other 2/3 don't exist anymore. So now I want to do 5 sevenths of that. So now I'm going to shade in 1, 2, 3, 4, 5. Now, how many total blocks are there? 21. Yes? Because there's 7 this way, and then 14, and then 21. And how many of those are double cross-hatched, or double shaded? 5. So sure enough, 5 sevenths times 1/3 is 5/21. Now, the minute, do you see how a student could understand like denominators at first and do 1/2 plus 1/4, make it 1/2 plus 2/4. But then you show them multiplication, and then they start to forget that it isn't this, right? Because multiplication, we just multiply straight across. Y'all with me? Now, me, being that I taught people that already have seen a lot of math once they get to me. They've normally seen a decent chunk of algebra. I can explain this like this is x plus x squared, for example. Can I add those? Are those like terms? Can you add x plus x squared? You can add x plus x. What's x plus x? 2 x's, right? What's x squared plus x squared? Do I have any x4s? Did I just say any x4s? X to the fourths. So what's x squared plus x squared? 2x squared. What is x plus x squared? I don't know. That's it. That's what it is. You with me? So, when you add and subtract fractions, like denominators are necessary, because like terms are generally necessary for addition and subtraction. Can you do x times x squared? Yes, you can. What's x times x squared? X cubed. Multiplication and division are a little more relaxed. They don't need perfectly like terms. I don't know if you guys are with me or not. Again, unfortunately for you, you're not going to necessarily be able to explain it that way to somebody who has never really worked with x directly before, right? Okay, maybe. Does this here make sense? And again, if it was this way, I would have just drawn 5/7 first and cut it 7 ways this way, and you can show that it is commutative, right? I spoke the other day about addition, subtraction, fractions just inherit all of the properties. Same thing with multiplication, division. They just kind of inherit all the properties. We'll talk a little bit more about that because there is one new property, a little bit new. Okay. How would I do this type of problem with mixed numbers? How would I do a mixed number in this way? So let's say, for example, what do you got, Jeff? 1 1/5 times 2 2/3. Yeah.
Would you want to put them into improper fractions first?
You could, but let's say that my instructions are don't do that. Nah, sorry. Even then, that would actually make it a little more challenging because I want to draw this, right? And that would be top heavy, it'd be a little weird to try to draw that. So this actually is a better form for visualization. So real quick, I don't know if you guys remember, back when we did like 42 times 17. So we had, you can do it, Jeff. 42 times 17. So there's 42. Yeah, times 17, there's 1, so that'll be 100 right there, right? That'll be 100, 200, 300, 400. I don't know if you guys remember that we did that. And you can actually use the flats and the longs and so forth. So this is 10 times 10, 10 times 10, 10 times 10, 10 times 10, 4 times, of course. And then this will be, blah, blah, blah. So you can keep going. Here, I'm going to have 1 1/5 times 2 2/3. So this will be that. Okay. So of course it's not to scale. You try to kind of represent it. I don't know if you guys are all with me. So when I did 1, I did about 1/5 of it. Bam, 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 bam. So this would be like this. So you do this times this, this times this, and then this guy is going to be like this and this. Now what the shit does all that mean, Jeff? Well, this is definitely a 1 and this is definitely a 1. Right? This was 1/5 by 1. So this is 1/5. This is another 1/5. Really, do you guys understand what's happening? So isn't that 1? Okay, real quick. This is a whole 1, correct? And this is a whole 1 and another whole 1 because I got 2 there, right? So 1 times 2, 2. I love it. This is 1/5 long by 1. So it's 1/5 times 1, plus 1/5 times the other one. So this is 1/5 of 1/5. This was 2/3 times 1, so this is 2/3. This is 2/3 times 1/5. It should be a little skinnier, but it doesn't matter. What would this be then? 2/3 times 1/5. 2/3 times 1/5. 2/15. So then the answer would be 2 plus 2/5 plus 2/3 plus 2/15. Yes.
So this is the similar idea of the box or the rectangular array that we're doing?
Yeah,
Just
not really. Sort of. But again, if I'm gonna do mixed numbers, I can't have a single thing, right? So this is so this will be the 1 piece, and this is the 1/5. So there's 1 and 1/5. Here is 1 and 1, that's 2, and 2/3. So 1 times 1 is 1, 1 times 1 is 1, 2/3 times 1 is 2/3, 1 times 1/5, 1 times 1/5, 2/3 times 1/5 is going to be that little tiny dude. All very exciting. And now if I add those together, I should get the right answer. Now you can tell very quickly that this doesn't really help with the work. You guys see that? Because what do I have to do to add these together?
Change them into the 15ths.
Yeah, so this will be all 15. So this will be 6/15 plus 10/15 plus 2/15. So I get 2 and 18/15. So what is that? 3 and 3/15, which is 3 and 1/5. I like it. Now, real quick, if I were to remember that 1 and 1/5 is 1 plus 1/5, 2 and 2/3 is 2 plus 2/3. Oh man, this is so awesome. How do I do this kind of problem? What do I have to do? And again, this would probably be a few levels above possibly some of the students you're tutoring or teaching. How do I do that kind of problem? What do I do? Sure, but what's it kind of called? It's kind of nice. I don't like what we call this because we shouldn't have to call it that, but what do you wrap your potato in before you put it in the oven? Foil. Okay, so it's, and I don't like foil because it's not in mathematics because I don't need it. I don't need the mnemonic device to help me because it's just repeated distribution. It's one of many things I wish we wouldn't make a little saying for because it's unnecessary. It makes it feel like, oh, I couldn't do it if I didn't know that. So what do we get? You get 2 plus 2/3 plus 2/5 become a 3 plus 2/15, which incredibly enough is exactly what we got down there, right? Okay. All right. Real quick, yeah, let me show you something related to this that's a little less, let me see. It is entirely possible that you will get a class where you actually have to teach some algebra. So believe it or not, this is actually going to be a little easier to visualize than what we just did. So if I have x plus 2 times x plus 3, right? So if I write, so this is x, this is 2, this is x, and this is 3. So this is x by x, what's the area of this? This is x by 3, so what's the area of this? This is 2 by x, and this is 2 by 3, 6. And sure enough, when you FOIL x squared plus 3x plus 2x plus 6, right? That's effectively what we're doing with those fractions, correct? So even before they understand FOILing, they've done this kind of thing before with base 10 kind of pieces, lining them up the same way. This is one way you could show FOILing to somebody that you're just teaching algebra to, right? You guys with me? Because obviously the biggest mistake I see is somebody tell me it's x squared plus 6, which leaves out these poor little dudes, right? Okay. Where are you? Oh yeah. Yeah, I could do that. Yeah. Okay. Okay, that's right. The problem we just did, this guy. Let's do like somebody suggested. Let's change these to improper fractions. What do we get? 6/5.
And 8 thirds.
Yeah, good. 8/3. All right. We're going to play around with this a little bit. We're going to do weird things to this. We're not going to get the answer. We're just going to play this a little bit. 6 times 8 over 5 times 3, correct? Unbelievable. So instead of multiplying stuff, we're just going to do something real quick. You'll see the point that I'm trying to get to. Each of these, the top and the bottom, they are whole numbers. And this is what I meant by the properties of whole numbers just get inherited by fractions. Because aren't I allowed to flip this? Because whole numbers, of course, have what property? If I just change it, what property is that? If I just move where the numbers are? Commutative. Associative is when you have parentheses moving around. Yeah, individuals commute like we did. So individuals commute, parentheses associate. Okay. And of course, why would you even want to ever do this in this weird ass way? Because what does it show? That this is actually equal to 6/3 times 8/5. And 6/3 is 6 divided by 3 is 2. And of course, at this stage in your life, if you see this, I would hope to God you would just do this, correct? Shit, yeah. Let me make my numbers smaller before I go multiplying everything. You guys agree? If I got to do a problem and I can make the number smaller, yes. But again, don't just show somebody, yep, that's how it works. This is one level of showing why that makes sense. Why does that work? It's because of the commutative property that would happen. So this just becomes a shortcut. Because this is 2, which is exactly what you would get here, 2 times 8 divided by 5. Right? See everybody? Nothing amazing. But again, you got to connect what they understand with where you want them to go. And then, of course, this we can write in improper and get the same answer we got earlier. I mean, mixed number. So what this leads to is this kind of silly little fact. If I have A over B times C over D, this equals to A over D times C over B. All right. So that's kind of like an intermediate step before you get to the full shortcut, right? Okay. So here's the one thing that I don't know if I think we talked about this before. Remind me, guys, what's additive inverse? What's the additive inverse? So if I give you a number, could you tell me the additive inverse? So if I give you the number 3, what's the additive inverse? possible you didn't talk about that. All right, it's very possible you didn't talk about it, so I'm sorry if we didn't. So if I want the additive inverse, in fact, now that I think about it, this book probably didn't talk about this yet, because it doesn't say negative numbers exist yet. So really, the additive inverse is the number I would add to something to make it become the identity. What's the additive identity? That we know. 0. So what would I add to 3 to make it become 0? Good. So there is no subtraction, there's just adding the additive inverse. What about multiplicative inverse? So what's the multiplicative inverse of 4? Well, what's the multiplicative identity? What do I multiply to make something stay the same? 1. So inverse of an operation is the thing that I operate on, using an operation to get me to that operation's identity. It's a lot of words. So for additive inverse, it's just what do I add to get 0? Multiplicative, what do I multiply by to get 1? So what would I multiply 4 by to get 1? 1/4. All right, this is where I get students when I teach this to somebody, they say, well, you don't multiply, you divide. I'm like, okay, what do you divide by? 4. And what's division by 4 the same as? Oh yeah. So this is an example, there is no division. There's only multiplication by the inverse. Okay. Don't tell that to the little ones, right? We don't want to tell them that too early. Subtraction kind of has its own approaches, so let them believe that it's its own thing. Okay, so what's the multiplicative inverse of 2/7? That's crazy.
So you just multiply by the reciprocal?
Yep, totally. So another name for the multiplicative inverse, reciprocal. Kick ass. So that's one, I can't remember. I'm pretty sure we talked about multiplicative identity. That's exactly right. We didn't talk about multiplicative inverse because that required us to have fractions defined. And I'm really sorry. We did not talk about additive inverse. I always kind of forget. This book pretends negative numbers don't exist at first. Yeah. Oh, I did that. Okay. So now we get to some nifty shit. So what about... We talked about this a little bit already, but division. So this is what I was talking about before. It's really easy to come up with a physical situation that can be modeled by 4 times 2. But what would the physical situation be that would be modeled by 4 divided by 1/2, right? Okay, so we're getting there. So let me write this down. So if I had 64 apples, divided evenly across 4 crates. How many apples per crate? So this is a physical situation involving division of whole numbers. So that you can come up with, that's easy. So what is the answer? 16. So it'd be 64 divided by 4 is 16. Kick ass. Now, that's the easy step. So here's what I came up with. What if I had 8 apples evenly distributed across each half of a crate? So the way I kind of came up with this first, I want to keep my language consistent, but the way I came up with this first was, what if you knew a crate was full, but half of it was covered, and you see 8 apples? How many apples would be total in the crate? So that would be 8 divided by a half is 8 times 2 is 16. So there is a physical problem involving division by a fraction. Because what did we do here? We divided 64 divided by 4. Right? If I would have made this 8 crepes, sure. It would have been 64 divided by 8. So I made it freaking half a crepe. So it's got to be the same thing. The process in mathematics almost always does not give a shit what the specific elements are. I don't know if that makes sense. So if I said what's 2 plus 3, it's 5. If I said what's 1/2 plus 1/3, the process says you add those together. Give me what that totals to be. We care that they're fractions. Math doesn't give a shit. It's still just addition. So here, 8 apples distributed across half a crate is 8 divided by a half. And the student's going to know, if you told a student this, they can pretty much figure out it's going to be 16. If I uncover the other half, there'd be another 8, 16. So somehow 8 divided by a half should come out to be 16. And of course, all of us in here should know it's multiplication by the reciprocal, so of course that works. And I think I showed you guys one exciting way to look at why it's multiplied by the reciprocal, right? You write that complex fraction, which you would, you never should do. There's no reason, but it's just a way to see why it works. Okay. Okay. So that's a little side note. So let's go back to, so now we're getting fully into division, which is a little funny because the whole idea of a fraction is division. But now we're talking about dividing fractions. Oh, good job. I got plenty. Thank you. What about if I have, let's go back to yeah, let's look at this one more time. Sounds great, Jeff. This is exciting. We looked at this one way, which was that's the number that it takes 2 of to add to be 6, correct? Another way to look at this is how many 2's fit into 6, right? So that sort of naturally leads to this. So I got 1, 2, 3. Pretend like my scale is good. So again, that's a nice visualization of 6 divided by 2. 3 2's fit into 6. So that's why the answer is 3. So of course, if I have something like, let's start off nice. 6 7ths divided by 2 7ths. Can you try to draw, just like I did, a number line to represent this? So like this one, I would take the number on top. So how'd you guys do it? Here's 0. What's over here? 1. Could be 1. Yeah, let's say 6 7ths, right? So I can put the number on top. I can make that the whole thing. Right, and then of course I want to cut that into 3 parts, right? So what must each of these be? So that at the end it makes 6 7ths. 2 7ths. Or better yet, I already know 2 7ths. So if I go 1 step of 2 7ths, 2 steps of 2 7ths, 3 steps of 2 7ths. Right, so that would be the answer is 3. So I already knew 2 7ths. So if I just start putting 2 7ths down, I can just see how many does it take until I get to the end, until I get to 6 7ths. Does anyone understand that that is a special case? This fraction is really, really easy to do, right? Because it's just like 6x divided by 2x. Well, that's 3. 6 of these divided by 2 of these is 3. Maybe? Okay. So in the special case where the denominators are equal, So if I have A divided by B, A over B divided by C over B, who can tell me what the answer would be? A divided by, well, A divided by C, right? Isn't that what this happened? 6 divided by 2 is 3. The 7 sort of didn't matter. Okay, I like it. And of course, we know how this would work, right? How do you divide fractions? What do you do? This would be 6 sevenths. How do you divide fractions? What do you do? Times. And what do the 7s do? Cancel. That's why, behind the scenes, that's why this works, of course, right? Okay, I like it. But the nice thing is, when you teach students, for the first place, what just straight up division means for whole numbers, part of what it's going to show them is the idea of the sharing and the measurement method, right? So how many 2's fit into 6? That gives you 3. So you can do the exact same thing with this before you even show them the shortcut. They don't have to know this to get that. 3 of these fit into that. They can see that. So, real quick, this kind of leads to another, what the book would call intermediate algorithm. You better guess. So real quick, go with me. What if I had 2 fractions that I was dividing that did not have the same denominator, right? Well, if they did have the same denominator, I have a shortcut, don't I? And this is before I know about the multiply by the reciprocal thing, so I don't know that yet. How can I make them both have the same denominator? What does the first dude need? What does he need that the other guy's got? What does he need on the bottom that the other guy's got? A D. What's he need? A B. Now can I use the shortcut? The bottoms are the same, correct? So what do I get? And this is A over B times D over C, correct? If I go like one step back. So the original problem was A over B divided by C over D. So here's a whole other way to show why division by a fraction becomes multiplication by the reciprocal. It's right there, right? So normally a student will kind of really be able to see this decently well, especially if you've really built the idea of fractions and working with number line with fractions. They can see when the bottom's the same, then it's pretty straightforward to divide. So when the bottoms are not the same, this is what I would end up with, and that leads to the shortcut. There's a whole other way to show them why division becomes multiplication by the reciprocal, right? You don't have to do it the complex number method that I did. I showed you a while back. Yeah. Blah, 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 blah. Oh, yeah. So what about here? Yeah. What if I asked you to, I feel like I missed something. No, okay. Do this, but I want you to use the missing factor approach. Oh shit. So how does that work? Well, let's see. Let me get you guys started. Can somebody tell me what the answer should probably look like? What form should it take? Don't tell me what the answer is, but it should look like a, you're like, what is he doing? It should look like a fraction, right? So let me just write a generic fraction. There's my answer. My A's look like 9s. Kind of sucks. So does anyone remember how the missing factor approach works? So just to remind you guys, if I have 10 divided by 2 equals something, the missing factor approach says that's the missing factor that 2 needs to become 10. And they've got their multiplication tables memorized, so then that becomes a much easier problem. 2 times 5, oh yeah, this is fine. right? So that's basically what we're gonna do here. This would mean that 28/45 would equal 4/9 times A over B. Now, of course, what is this? Four A over 9B, love it. Now, this one's cheating a little bit. You guys might be able to tell because the numbers work really nice. But again, you're gonna pick some nice examples when you're first starting to talk about a concept. So what would A have to be? Well, 4A has to equal 28. So A has to be 7. And what's B have to be? 5. So you get 7/5, right? Notice this. Does everybody, semi-decent with that? Everybody understand that the numbers are nice. If I just change each of these by 1, this whole thing kind of gets really weird. Y'all agree? Okay, so this is a easier problem. But this leads to something. This leads to, how can I make this into a shortcut now if the numbers all kind of like work together? I want you guys, can I just look at the top? What is 28 divided by 4? 7. What's 45 divided by 9? 5. So if the numbers work well together, that kicks a lot of ass, right? Everything kicks a lot of ass when the numbers work well together. Yes?
So even if you were to do like the reciprocal, like.
Yeah, let's see. So 28 over 45. This better come out to the same answer. This whole thing's shit, right? So I appreciate that. You're like, all right, Jeff. So 4 goes into 28. 7 times 9 goes into 45. 5 times 7/5. Sweet.
So is that what you're saying when you mean like if it didn't work out perfectly?
Yeah, then these wouldn't have gone in completely, correct? But let me see. What you're trying to do is you're trying to get them to a point. Let me show you. And again, listen. I need you to understand it. And we've done this a lot. There's a lot we're gonna look at that we would never do. We don't need to anymore because we understand this shit. But everything that we're doing is making a connection between what they already have seen and where they need to be. So every time I teach a class, I'm always like, okay, what should they know now, and what do I need them to know by the end of the day, and how can I connect that, right? Okay. So that's the kind of problem where they would kind of eat that up, and again, it's because the numbers work really well. So what if they don't? So what if I have, for example, what do you got, Jeff? Sure, 12/35 divided by, well, the top works, but let's make the top not work. Yeah, let's make it 7/10. Well, it's okay. That's gonna work. All right, so let's see if you guys get this. What I want is this to be divisible by this and this to be divisible by this. Is that currently true? I'm totally allowed to multiply top and bottom of a fraction by anything except 0, correct? So I really want this to make sense. All 12 needs to be divisible by 7 is 7. Does that make sense? If I multiply 12 by 7, is that divisible by 7? By definition, correct? Anything times 7 is divisible by 7. You guys with me? Because I gave it a factor of 7. All right. Now 35 to be divisible by 10 actually only needs 2. Does that make sense? It's already got a 5 in it. But what we normally do, watch this. So if I do 12, all 12 needs is a factor of 7. So I got to do this, correct? Now the top is happy. The top is going to work if I go straight across, correct? Now, ignoring the 35. If I multiply both by 10, now the bottom's going to work. Do you agree? And the whole reason we had to do that is I can't multiply top and bottom of a fraction by different things. So if the top and bottom need different things, they both get all of it, because that's the only way to make it work. So now what happens? What's the top? What's 12 times 7 times 10 divided by 7? 12 times 7 times 10 divided by 7. Don't.
12 times 10.
12 times 10, thank you. And what's 35 times 7 times 10 divided by 10?
35 times 7.
Cool. And isn't this 12 35ths times 10 over 7? Right, and you're all like, oh God, it's another freaking way to show. And again, what kills me is there are teachers out there. I have seen this. There are teachers out there that will just teach you flip the second fraction and they don't explain why. You with me? Students will be able to do these problems all day, but they have lost a part of what's supposed to be their foundation. They start to believe, oh yeah, just whatever the hell the guy says, that's just what it is, right? They need to start to have an expectation that the dude or dudette at the front of the room is going to be able to explain why all of the shit they do works. Instead of just, whatever this person says, yeah. And then, of course, I almost don't care what the answer is. It's just, again, it's just showing that division becomes multiplication by reciprocal. I like it. Kick ass. Okay. Couple more things, and then we'll head out a little bit early. Some of us already did. That's okay. These things happen. All right. I know. It's, as a math teacher, you get very used to being a very boring person. But these things happen. So let me come back to what you're gonna, let me see. If I were a student here, I would count on. All right, 6 divided by 2. All right, so that means how many 2's fit into 6, right? So if I do 3 divided by, let me not write like that. If I do 3 divided by a half, another way to look at that is how many halves fit into 3, right? So again, if I wanted to, I could do a number line kind of idea. So here's 1, 2, and then there's bam, bam, bam. So how many halves fit into 3? 1, 2, 3, 4, 5, 6. Sweet, right? Very visual, counting elements, right? This is sort of like what I was talking about, which I don't know if it made any sense to you, but it's, we base everything off of 1, and we don't have to. I could base everything off of a half. And then halves would make as much sense as 1 does. No idea if that makes any sense to you guys. It almost doesn't matter. So here I am, basing things off of a half. So how many halves fit into 3? 6. And of course that reinforces that's 3 times 2, right? What about this? What about 4 divided by 2/3? So what I'm going to do here is I'm going to use a bit of a region model to help me. So I'm going to draw a 4 first. Here's 1, 2, 3. Good Lord, Jeff. 4. Okay. So I drew a representation of 4. What do you think I'm going to do now with all the parts? Cut them into thirds, 11. Even if you're not sure where I'm going to go with this, that kind of makes sense, because it's based on some kind of thirds, right? This is, to me, again, very often I'm the only person in the room that finds certain things interesting. But this is really kind of cool. Now I'm trying to see how many groups of 2/3 are in 4. So you guys try. Can you find, I'll start off. Isn't this a group of 2/3? Keep going. How many groups of 2/3 can you get total? Yeah, so there's 1. You can go across. These can now be cut apart. I actually chopped them. So this will be 2, 3, 4, 5, 6. Now, real quick, do 4 divided by 2/3. What is it? 4. Yeah, it's going to be 6. I know, but so it'll be 4 times 3/2. 2 goes into 4 twice. 2, 3, 6. Sweet. That's a cool little visual, right? That sort of also goes along with my stop looking at things as one, start looking at them as 2/3. So 6 groups of 2/3 fit into 4. I like it. Okay. What was the other one? Oh, there it is. Yeah, that gets a little weird. Oh, good. Okay. All right. Last little thing I want to say. Can you calculate this mentally? By the way, if you haven't caught on to this, on a day when I'm doing a lot of talking, which is always very exciting, the next day I try to start off with a little group work kind of thing, right? So you can kind of practice all the stuff I spewed at you the day before. What do you guys think about this? I want you to do this mentally, right? What approach are you guys taking? I'm going to take the wait and see if anybody else has something approach. Let me remind you guys about something. One thing is, isn't this 24 plus 4 sevens? Does anyone remember an interesting application of the idea of distribution? This is a very obscure thing, and I don't blame you for forgetting this, but if the division is on the right, it can distribute across. Because all that is, isn't this 24 plus 4 sevens divided by 4? Isn't that the same thing? And isn't that 24 over 4 plus 4 sevens divided by 4? So it's easy. What is 24 divided by 4? 6. And what's 4 sevens divided by 4? How many sevens? If I have 4 sevens and I divide them by 4, I now have, if I have 4 chairs and I put them into 4 groups, how many chairs in each group? 1. So if I have 4 sevens and I divide them into 4 groups, there's 1 7 in each group. Don't forget that. Dividing a fraction by a whole number is nowhere near as difficult as it looks. So one quick thing I want to say about that. 4 sevens divided by 4. You can either look at that as like 4x divided by 4 is x. So 4 sevens divided by 4 is 1/7, the same way. Or, what am I dividing 4 by? I'm dividing 4 by 4 and 7. So I'm dividing 4 by 28. And what's 4 over 28? What's that reduced to? 1/7, same damn thing, right? So I don't blame people for not liking, this is a complex fraction, a fraction inside of a fraction. They look disturbing, right? But they are nowhere near as difficult as people make them out to be. But why are they difficult then? Because we don't use them very often. We don't see them a lot. So when they show up, it's like, what the shit? It's sort of like Virginians and snow. I used to live in Virginia. Whenever it snowed, you just didn't go anywhere because some idiot was going to be like, I can do, oh shit, flipping around. Because we didn't get a lot of snow. So when it came, we didn't know what to do. San Diego, it's rain. When it rains, people are like, what? Sorry. Now I'm one of those people, so I've been here long enough. All right, guys, that's enough. We'll stop there. That's fine. So next Tuesday, we'll start with a quiz. I'll have a little handout so you can practice some of the stuff at the start. But today, we'll get into chapter 7. Yeah, sounds good. Sam Arms, up there? There.